Our work, Post-Training Quantization for Referring Image Segmentation, proposes a novel solution focused on developing and deploying RIS tasks for edge devices such as intelligent robots. The RIS task input the picture and natural language expression, extract the visual and linguistic feature through the visual encoder and the text encoder respectively, then use cross-modal attention fusion mechanism for feature alignment, and finally generate the mask of the specified object through the decoder part. However, the complex architectural design of RIS models inherently requires a lot of computing resources and high-performance GPUs, so we propose to quantify the model to deploy the guide in limited hardware resources and robotics platforms. Upon directly applying existing quantization methods to the full precision model, we observe a significant performance decline. So we analyze each module of the RIS model individually and identify that the visual encoder and text encoder are particularly sensitive to quantization. For the visual encoder, we observe that the activation distribution after the softmax and Zhou function significantly deviates from a Gaussian distribution, leading to substantial quantization error when using a single scale. Therefore, we adopt the dual-region quantization (RORQ) method to quantize the activation in both ranges separately. For the text encoder, we find that the activation is significantly affected by numerous outliers, especially at lower bit widths. Thereby simply suppressing these outliers can result in a collapse of model performance. So, we propose a reorder-based outlier-retained quantization method, which iteratively partitions the activation values into groups and dynamically quantizes each group using distinct scale factors. We developed the basic model, RTN, and re-implemented advanced PTQ methods designed for image classification tasks, namely PTQ4RIS and REPQVIT, and we conduct comparative experiments on 3 benchmark datasets using different bit widths, and the settings demonstrate the effectiveness and superiority of our PTQ4RIS. The visualization results show that our model not only outperforms other methods in performance, but also shows that the size and inference time of the model are reduced to some extent under different bit width settings. Finally, some qualitative results are presented.